All right, welcome to this explainer. We've designed this as your ultimate exam study guide to help you really master the epic, evolutionary struggle between switching speed and power consumption in digital logic. If you've ever wondered how we got from these power-hungry, incredibly noisy circuits to the ultra-efficient microprocessors sitting in our pockets right now, well, you're in the exact right place. We're going to map out the entire family tree of digital logic, breaking down the characteristics, the fatal flaws, and the brilliant solutions engineers came up with at every single step. Here's our quick syllabus for today. First, the logic building blocks. Second, early attempts and flaws. Third, the bipolar era. Fourth, the CMOS revolution. Fifth, BiCMOS, the ultimate hybrid. And finally, the rules for interfacing families. Let's get right into it. Section 1, the logic building blocks. We had a look at the physical components first. Think of this table right here as your foundational recipe book for the exam. You literally need to memorize which components construct which family. So we move from the super simple diode logic, which uses just diodes, all the way into the resistor and transistor combos of RTL and TTL. And then finally at the bottom, we hit the modern era, which relies entirely on MOSFETs for PMOS, NMOS, and CMOS designs. How these specific components are wired together, that completely dictates how fast the circuit can switch, and crucially, how much power it wastes as heat. Now, to build a solid mental map for test day, you can actually split the entire logic world into two main architectural trees, unipolar and bipolar. Unipolar families, those are the ones up top, use MOSFETs that rely on just one type of charge carrier. Simple enough, right? Then down below, we have bipolar families. These use components relying on two types of charge carriers. And as you can see, those branch off even further into saturated designs like TTL and non-saturated designs like emitter-coupled logic. Keeping this visual hierarchy locked in your head is going to make classifying questions a total breeze. Section 2, early attempts and flaws. Let's talk DL, RTL, and DTL. So, diode logic. It was the absolute simplest architecture you could possibly build. But man, it came with some massive drawbacks. Think of its voltage degradation like a really weak flashlight beam that just kind of fades out over a distance. It literally couldn't push signals very far down a circuit board. On top of that, it had terrible fan-out. That means a single diode logic output could barely drive the inputs of other gates without the voltage drooping completely out of spec. Oh, and fundamentally, you couldn't even build an inverter with it. For complex computing, that is an absolute deal breaker. So engineers realized they needed to move to transistors, but those early attempts were, well, they were messy. Take resistor-transistor logic, or RTL. Imagine trying to have a really detailed conversation in a crowded, incredibly loud room. That is exactly how RTL experienced electronic interference. It was so incredibly sensitive that it often malfunctioned just because someone flipped a switch in the same room. No way you can build a reliable computer like that. So they created diode transistor logic, or DTL, to solve that hilarious vulnerability. By taking basic diode logic and adding a transistor, they drastically reduced the power draw, bumped up the speed, and completely fixed those ridiculous noise immunity failure modes. Moving on to Section 3, the bipolar era. This is where we meet the heavyweights like TTL and ECL. Enter transistor-transistor logic. You will see this universally referenced on exams and datasheets as the standard 7400 series. Seriously, if you see a chip starting with 74, you are looking at TTL. This family became the absolute standard workhorse of the entire industry because it finally struck a manageable balance. It was noticeably faster than RTL or DTL, and it settled right into this nice medium zone for power dissipation. Was it perfect? No, but it was incredibly reliable. And if we trace the TTL timeline, you'll notice how all these subfamilies emerge to continuously tweak and improve that speed-to-power ratio. You start with the totally obsolete 74 series on the left. But then, look at how the paths branch out to the Schottky series, or 74S, which prevented deep transistor saturation to really boost the speed. That then evolved into the fast, or 74F series. And get this, 74F is still widely used today. That's all thanks to massive innovations in IC design that dropped power dissipation while keeping the switching super snappy. But what if you didn't care about power consumption at all? What if you literally just wanted raw speed? Well, if TTL was your reliable everyday sedan, emitter-coupled logic, or ECL, was a Formula One race car. Because it's a non-saturated bipolar logic, it is hands down the fastest family available. But exactly like a race car, it burns a massive, totally inefficient amount of fuel, in this case, electrical power. It burns through it to achieve that speed, dumping a ton of heat in the process. It also suffers from a really low noise margin, meaning it requires some incredibly precise engineering just to keep the signals clean. So here is your ultimate cheat sheet for memorizing family characteristics. This historical trade-off is absolutely crucial. Notice the pattern here. You could either have incredible speed with ECL, but you'd suffer massive high power costs. Or you could have medium power with TTL, but you'd have to sacrifice that top-tier speed. For decades, engineers were literally trapped in this box. You simply could not have both. Which brings us to Section 4, the CMOS revolution. Time to break the rules. Complementary metal oxide semiconductor, or CMOS, famously known as the 4000 series, completely shattered all the rules. For the very first time, engineers achieved both high speed and low power consumption. It had excellent noise immunity and a massive fan-out. To conceptualize CMOS fan-out, think of it like a single, highly effective teacher effortlessly managing a massive classroom of hundreds of students without even breaking a sweat. It can drive numerous inputs just effortlessly. Its only real Achilles heel, it's highly susceptible to electrostatic discharge. A simple static shock from your finger could literally fry the chip. Now listen up, because if you want an easy point on your exam, make sure you highlight this specific fact. While CMOS is incredibly efficient when it's just sitting there, its power usage is not static. Its power dissipation depends heavily on its operating frequency. Basically, the power usage is going to spike significantly the faster you run its clock. So it sips power when idle, but man, it gulps power when it's switching back and forth millions of times a second. Because the tech world was already running heavily on the 7400 TTL standard, engineers had to make CMOS play nice. Following this flowchart, you can see how the original 4000 series actually evolved into the 74C and 74HC lines. Why? Specifically to become pin and voltage compatible with older TTL systems. They drastically increased the speed and fixed the output drive capabilities so you could pull an old, power-hungry TTL chip right off a board and drop a highly efficient CMOS chip right in its exact place. A total game changer. Section 5. By CMOS. The ultimate hybrid. Erasing the compromises completely. Enter by CMOS. Just like the name implies, it is the ultimate bridge in our evolutionary story. It fuses the blistering, heavy-duty driving speed of bipolar junction transistors with the energy-sipping, ultra-low idle power of CMOS logic. When you need heavy bus interfacing applications that demand low power but blazing high speed, by CMOS is the absolute gold standard. It completely erases that traditional speed versus power compromise we talked about earlier. And finally, Section 6, Rules for Interfacing Families, your troubleshooting guide. For the practical troubleshooting portion of your exam, you absolutely must know the strict rules for physically connecting these different logic families together on a single board. You can't just wire them up blindly. Here is your step-by-step troubleshooting guide. Step 1, you must verify the voltage specs. A 5-volt TTL chip just isn't going to talk nicely to a 3.3-volt Lautern CMOS chip natively. Step 2, verify the current limits and fan out to ensure you aren't overloading the output pin. And step 3, if those voltage standards do differ, you have to insert additional discrete elements, like a pull-up resistor or a level shifter, to ensure compliance and prevent a catastrophic circuit failure. To really conceptualize this failure mode, imagine two people trying to talk, but one is whispering and the other expects a shout. If a TTL chip outputs a high signal at 2.4 volts, but the CMOS chip receiving it demands at least 3.5 volts to even recognize a high, the receiving gate simply won't hear the signal. The circuit will just fail silently. No smoke, no sparks, just failure. This is exactly why matching those voltage tolerances is the absolute golden rule of interfacing. So as you wrap up your studying, review those component tables, trace that evolution from noisy diode logic all the way to the brilliant bi-CMOS hybrid, and ask yourself this: now that we've merged the absolute best technologies to conquer both speed and power, what physical barrier will engineers have to break next? The world of electronics never stops evolving. Good luck on your exams, and I'll catch you on the next explainer.